Okay, let's get started. So you got homework. I pushed the web work back to 9 a.m. Wednesday. So you have till before class 9 a.m. Wednesday to finish this because a lot of today's stuff pertains to that web work. So I wanted to give you more time. So we're focusing on sequences now. What is a sequence? What is it? What is a sequence? What's that? Okay, yeah, so yeah, ordered set or a list, right? So it's a list, right? It's a list, ordered list or an ordered set of values. And so now we're looking at, if we look at that list, particularly an infinite sequence, like an infinite sequence, we're saying, does the sequence converge? And what does that mean? What does it mean for a sequence to converge? Maybe talk to the person next to you. What does it mean for a sequence to converge? Maybe just street talk, but also a mathematical version, right? So both, what does it mean, like understanding it and mathematically? Okay, volunteer. What's the general idea of a sequence that converges, an infinite sequence that converges? What's the general idea? Any volunteer? The list of numbers does what if it converges? Yeah.
It tends to become one indistinguishable number.
Okay, right. So it's like the values get closer and closer and closer to a particular value. That's what it means for a sequence to converge. Those numbers are getting, they get indistinguishably close to each other, and so that means they're honing in on a particular value. And then mathematically, you can pick any degree of closeness. This is what we talked about before. You can pick any degree of closeness. And then eventually in the sequence, you get within that degree of closeness and you never leave it. But then you can pick a higher degree of closeness. And then eventually in the sequence, you'll get to there. So you pick any degree of closeness that you want, as small as you want. And eventually that sequence, those values will get within that degree of closeness to the limiting value and then never get further away. Okay, but that's for any degree of closeness, right? So it's like the values getting infinitely close to a particular value. That's what a conversion means. So how do we analyze these? So we talked last time about geometric and PE sequences, and we kind of derived general rules for those. Remember, a geometric sequence was? Geometric sequence was, form is r to the I, right? Constant value, index is the exponent. So basically, as you keep going down the sequence, you keep multiplying by one more r every time. It's like you keep it's a repeated multiplication of this constant value r, and the ith term has I of those multiplied together. All right, P sequence, what was that? 1 over I to the P. And when did a geometric sequence converge? So we looked at examples and we talked about why this works. So yes, you have to understand it, but you have to memorize it too. It's both. You have to understand it and memorize it. So boom, when does a geometric sequence converge? When? To 0, when r is between 1 and -1. That's what you should be thinking. Converges to 0. Converges to 0 when you keep multiplying a fraction times itself again, right? This is going to eventually get very, very close to 0, as close as you want to 0. All right, what about this? When does this converge? Positive. Any positive value for p means 1 over I to the p will converge. All right, and so we talked about limit function techniques, properties of rational functions, comparing the degree of the numerator and the denominator. I'm not going to go over all that again, but that's important. All right, I went over the very last thing, Hopital's rule. Just briefly, if you're taking the limit as I goes to infinity of, say, f of that equals the limit as I goes to infinity of the ratio of the derivatives if f over g goes to either 0 over 0 or infinity over infinity. These are called indeterminate forms. Indeterminate forms. Okay, if you've got a ratio and looking at that limit, you get 0 over 0 or infinity over infinity, that's indeterminate. It could be anything. So to help you determine what it is, you could take the derivative of both and take the limit of that sequence. The limit of that sequence will be the same as the original sequence that you were working on. But only in the case when you have an indeterminate form, 0 over 0 or infinity over infinity, as I gets big. Okay, that's yeah.
So maybe a situation where we have to perform multiple.
Do it again? Yeah, you could. You might have to do it again. So yes, you can. And if this is 0 over 0 or infinity over infinity, you could take this derivatives again. Take the second derivatives of f and g. Yep. Okay, and then listing out the first several terms. Okay, general algebra, pre-calc knowledge, and deductive reasoning and logic. So there's kind of a balance of this. There is like reasoning and logic, and then there's like these rules and like formal mathematics. There's both to this, right? And so there's the balance. We always want to show things mathematically, but you're gonna think deductively. Think about reasoning, like what's happening in the listing out the first several terms. What's happening, right? What's happening? You want to take that into consideration as well. Okay, so this is kind of our like sequences or like toolbox for finding convergence of sequences or divergence. Any questions on those? We're going to just do examples today. Ready to go? So here's what I want you to do. You're going to take some time to do this. You're going to write out the first 3 terms of each sequence and then analyze each one as convergent or divergent, and you're going to state your reasons or give kind of mathematical justification. If it's convergent, then say what the limiting value is, or determine the limiting value. What is the number that the terms are getting infinitely close to, or honing in on? Okay, so you get about 10, maybe 15 minutes to work on these. Look over your toolbox, right? Look over your toolbox. So you're looking for p-series, you're looking for geometric series, you're looking for rational functions, you're looking for possibly Hopital's rule if you have indeterminate forms. So I want to take attendance, but then we'll be walking around to help you. So you're making progress or you're getting help. Okay, let's see how you guys did on these. All right, Lily, you're up. How about that first one, -4 to the I? What did you say about that? Diverges. And what was the reasoning for that? Okay, -4, 16, -64. Okay. Okay, sure. Yeah, so these numbers are getting large, fast, also alternating positive and negative. So any other reason we could say this diverges? Yeah?
R is not between -1
And you're talking about what? What when you
or
say?
geometric.
Yeah, so you could recognize this as a geometric sequence with, so geometric sequence. Where R is, he said not between -1 and 1. So R is less than -1. And so that would be justification. It's a geometric sequence with R less than -1. And then what happens is what Lily described, right? So the numbers are just getting really, really big, alternating positive and negative. Clearly that can't converge on a particular number. Questions on the first one? Okay, who's up? Allison. How'd this next one go? Yeah, uh-huh. Okay. They're getting smaller. Okay, so are you saying it's convergent to 0?
Yes.
Okay, converges to 0. So we need some mathematical proof behind this. So what can we pull from our toolbox to do some mathematical justification? Only Anthony? Anybody else? Yeah?
Well, as the i's get bigger,
Uh-huh.
the sevens or the stat, the negative 7 or the -7, it's going to go or be irrelevant.
Okay.
Because it's so small.
Okay.
And then since we have I squared and 3i squared, they have the same power.
Okay.
It should be like 1/3.
So he's talking about inside the parentheses, as I gets large, we have a rational function with the same degree. So inside the parentheses, that's going to go to 1/3 as I gets big. Therefore,
Converges to sine of
he wants converges to sine of 1/3. What do you think? Yeah. If everything in the parentheses gets closer and closer and closer to 1/3, then this sequence is going to converge to sine of 1/3. Whatever that is. Does it make sense? Any questions on that one? So yeah, sine of 1/3 is a really small number, Allison, but it's not 0. So your deduction was correct, except that it doesn't converge to 0. It's going to converge to sine of 1/3. Okay, next one. 1 over square root of I. Spin the wheel. Here we go. Who's up? Kenny, you're up. 1 over square root of I. What do you think about that one?
I got convergent to 0.
And how? By what?
Because, well, your number on the bottom, as it approaches infinity, it's going to get increasingly bigger.
Okay.
So 1 is just going to be divided by a bigger number each time.
Okay.
It's going to be 0.
Yep, that's good reasoning. And then do we have a kind of more formal mathematical way to say this one? Yeah. P sequence. And what about this P sequence? It tells us this convergence to 0. So not all P sequences converge to 0. Only ones such that what? What does P equal in this case? 1/2, right? Which is bigger than 0. And so because P is 1/2 and bigger than 0, it does exactly what Kenny says. The denominator is infinitely large. Therefore, the ratio gets small. But this is a P sequence with P equal to 1/2, which is greater than 0. Questions on that one? Okay. Where is Alan? You're up. The next one.
So I said the sequence diverges
Right?
because the values do not get indistinguishably small. The farther along the sequence you get, for every difference between each term,
Yeah.
it's always 1.
Okay. So it's not that the terms don't get indistinguishably small. It's that
It doesn't
The difference between them. Right? So the terms can get really, really big.
I was going to say, well, I mean, that's what I meant. The
Yeah.
terms were getting smaller. They were going towards a number.
But that's two different things. So these could be approaching 1 million, and that would be convergent.
I know. I'm trying to figure out how to say it.
It's the difference between them.
Okay.
It's not that the terms have to get small, it's that the difference between them has to get small. Which you said after that. So it diverges because the terms don't get indistinguishably close to one another. It's not that the terms themselves have to go to a small number. They could go to 1 million. Like we could have, for instance, 897 I to the 10th minus 1 over I to the 10th plus I to the 9th. Does that converge or diverge?
That converges
To
897.
897. You see that? It converges to 897. And what gets small is the difference between subsequent terms, right? Eventually they're all just like 897, so close to 897 that we just called a day. And okay, good. Yeah, so this diverges because this will never get close to a particular number. These never get close to a particular number. Okay, next one. This square root one. And by the way, so Stephen pointed out a very important thing here. What about the first term? What happens with the first term here? Yeah, it's imaginary. So that's okay. We could allow for imaginary numbers in our sequence, and that's fine. As a matter of whether it converges or diverges in the long run, that doesn't matter that the first one is imaginary. It's a square root of a negative value. Okay, so now in the long run, what happens here? Gray, you're up.
So for that one, I said that it diverges.
Okay.
Just significantly getting larger and larger since the numerator is a higher power than the denominator.
Right. So it diverges because degree of the numerator greater than degree of the denominator. And does the square root help that in terms of divergence or convergence?
No, because it's applied to both numerator and denominator.
Okay, yeah. So it slows it down a little bit, but it's still going to get as big as you want, right? So square root is going to, maybe it doesn't get as big as fast, but it will get as big as you want eventually, okay? So this is a rational function, degree of the numerator greater than degree of the denominator, that will diverge. Okay, next one, I to the negative fourth. Nam, you're up. How did I to the negative fourth go? P. Okay. So P sequence. And what does P equal again? What does P equal in this? Careful. So this is the same as what? 1 over I to the fourth. Right? So what is P again? 4. Conclusion? Converges. So yeah, you had everything. Yeah, you were doing great. Just a negative exponent means positive in the denominator, so that's our P equals 4 converges. Questions on that one? Okay, doing good. How about this next one? Sebastian, how did it go? Okay, good. Okay, good. So this is the same as pi over 3 all to the I. Such a geometric sequence. Converges or diverges? Pi over 3. Between negative 1 and 1 or greater than 1? Greater than 1. Pi over 3 is a little bit greater than 1. Therefore, diverges. So pi over 3, 3.14 divided by 3. Happy belated Pi Day, by the way. 3.14 divided by 3 is greater than 1. Therefore, it diverges. Okay, how about this one? So one thing that's going to be really important in these problems is you have a really good concept of what exponent is. So when we say pi to the I, what does that mean? Just mathematically, what does that equivalent to? Pi to the I. Could you describe it to a second grader, what pi to the I is? Yeah, it's pi times pi times pi times pi. Space for pi times pi. It means multiply a bunch of pi's together. What's the I about? How many pi's get multiplied together? So we're taking I number of pi's multiplied together. That's what that means. I pi's. So we got that. So then what about what would then 3 to the I plus 1 mean? What would 3 to the I plus 1 mean? So how many 3's multiplied together?
It's I plus 1, so if you have like I out of 3,
Okay.
so you have to do that many and then another 3.
Right, exactly. So it's the same number of 3's multiplied together as we have pi's multiplied together. And then what else? Another 3. So we could write it this way. We could write it as 3 to the I, and then what? Times 3. This is super important that you can see that. Because it's like you got I number of 3's multiplied together, plus 1 would mean you multiply by one more 3. So what about this? We got pi. It basically is 1/3 of the one we just had, right? So this is pi over 3 to the I. Each one of those terms times 1/3. Diverges or converges? So this is still a geometric sequence. It's just all the terms are 1/3 as much as these terms. Therefore, converges, diverges. If these get infinitely large, just multiplying them all by 1/3 prevent that. No, it's just going to get infinitely large. 1/3 is fast, right? It's going to be 1/3 slower, right? So it's just going to take 3 times as many terms to get as large as this, but we've got an infinite number of terms that we can go with. So it's geometric still with r greater than 1. So this is essentially the same one as the one above. It's just they're all 1/3 of the ones, but then you can just take as many terms as you want and they'll still get as big as you want. So this one also diverges. Doesn't make sense. It's still geometric with r greater than 1. Any questions on these examples? Okay, a couple more. All right, I trust you can write out the first 3 terms. Let's skip over that part. But just the point is, you're keeping in mind that whenever you see one of these things, it's a list of numbers. That's why I have you write out the first 3 terms, because you're always keeping in mind that we're looking at these things. It's a list of numbers, and we're trying to figure out, does that list get infinitely close to a particular value? That's what we mean by it converges. Okay, so here's a couple more. Take a couple minutes, see how you do on these. What about this one on the left? What do you think? Converge or diverge? People are saying diverge. Agree? Because? But this is convergent, right? This is a convergent geometric sequence. But you're adding it to something that's diverges, right? So this, each term is here diverges. So what do we have? All the terms are a little bit bigger than the terms of a divergent sequence. Therefore, diverges. Okay, is this a geometric sequence right there? Is that geometric? Is that itself geometric? If it were geometric, then it would be some r to the I. Is it? No, you can't rewrite this as one number to the I. You can't rewrite this as, if you could, you're right. If you could algebraically rewrite it as one number to the I, it would be, but that's impossible. You can't do that. So therefore, it's not geometric, but we're using our knowledge of geometric sequences to answer it. And what we're doing is what's called a comparison. This is the idea of a comparison. What are we comparing this to? Which one? To make our conclusion, we're going to do comparison to what sequence? 2 to the I. How does our sequence compare to 2 to the I? All the terms are larger, right? Maybe not a lot larger, but they're larger. So if you have a divergent sequence and you make all the terms a little bit larger, you're certainly still going to diverge. Okay, so what about this one? So we got 3i plus 5 over ln of I. So I've written out some terms here. You can't, I equals 1, this is impossible. So we can't even have I equals 1 here because you get 0 in the denominator. But we need a mathematical, people are saying diverges, we need a mathematical, so this diverges. We need mathematical justification that this diverges. What do we got in our toolbox that can help us with this?
Natural log of I doesn't increase as fast as.
Okay, so that's good reasoning, but it's not like mathematical justification. But yes, right. This increases faster than this, but that's still that's kind of a good like check, or definitely good to think about. But if we wanted mathematical proof, yeah.
If we replace ln of I with I, that should make all the terms always larger. And then if that converged, then we would know that conversion.
You just want to change this to I? Yeah, we can't do that. That's a different sequence, right? That's a different sequence. What can we, yeah? So you want the derivative, like the quotient rule? It has to do with the derivative. We don't want to take the derivative of this. What do you mean? What do you want to take the derivative of? Right, now that's different. You're going to take the derivative of the, so what are you applying there? Yeah, so if I gets large, then the numerator goes to infinity, right? And if I gets large, then the denominator goes to infinity. What do we have? Indeterminate form. So this is a good one for Hopital's rule. That's what he's talking about. So we have, as I gets big, it's essentially affinity over infinity, which is indeterminate. That might be divergent. That might diverge. That might converge. It might converge to 0. It might converge to something else. So we're going to use the Hopital's rule. And we're going to look at the ratio of the derivatives, which would be 3 over 1 over I, which is 3i. So whatever the conclusion we have about this as I goes to infinity is the same as the conclusion about this as I goes to infinity. Divergence. Therefore, so three little dots like this means therefore. So this is the Hopital's rule. Derivative of the numerator divided by the derivative of the denominator gives us 3 over 1 over I, which is the same as 3I. That certainly diverges. Therefore, the original sequence diverges. Yeah?
I know what works is asking for us to state like if it diverges to infinity or negative infinity.
Okay.
For the ones that are like negative, like infinity positive, negative infinity positive, would it just be divergent?
Yeah. You mean the ones that alternate?
Yeah.
Yeah, neither. It's just, you can't say, yeah, because it's not going to, it's alternating between negative and positive, so neither. Neither, both, something. But you can't pick one of them. Okay, other questions about these? All right, factorials. Factorials, this is 4 factorial. It's not 4, right? Okay? This is a mathematical, it means this. It means start with a number and multiply down until you get to 1. Multiply down 1 less each time. So 4 times 3 times 2 times 1. That's what 4 factorial means. It always means that you stop when you get to 1. So this is 24. 4 factorial is 24. 4 times 3 times 2 times 1. Okay, by definition, 0 factorial is not 0. It's 1. Why that is a discussion for another time. We don't have time to discuss it. But just remember, 0 factorial is not 0, it's 1. All right, so this is the number of ways that you could put 4 things in an order. Choose how many ways for the first thing. Now you got 3 left, now 2 left, now 1. How many ways can you order 0 things? 1 way. There's 1 way to order 0 things. You just do nothing, okay? So that's one explanation about that. Okay, going on. 6 factorial equals 6 times 5 times 4 times 3 times 2 times 1, which is 720. Notice that that also equals 6 times 5 times what? 4 factorial. So in any factorial you have, as a factor of it, every lesser factorial is a factor of any given factorial. So within 6 factorial is 3 factorial as a factor, 4 factorial, 5 factorial, 2 factorial. Those are all factors of 6 factorial. Notice that? So that being said, what is 28 factorial divided by 25 factorial? So let's write it out. 28 factorial means 28 times 7 times 26. Okay, notice, so we could keep going here. So another thing we can do is, on these long ones, you can just go dot, 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 and then say 3 times 2 times 1, or 2 times 1, or 4 times 3 times 2 times 1, okay? But anyway, it's always going to go to 1. And then 25 factorial is 25 times 24, etc., times 2 times 1. So based on what we just said, though, so in order to simplify, in order not to have to multiply all those 2 huge numbers, right? The numerator and the denominator are just going to be both really, really big numbers. But to avoid that, we notice this fact here, that within 28 factorial is what? What is all the rest after 26 factorial? 25 factorial. And what's our denominator? 25 factorial. Therefore, this ratio is? What's left is, so 25 factorial is this part of 28 factorial, and the whole denominator is 25 factorial. So therefore, this whole thing is just 28. Because you have a 25 factorial in the numerator, 25 factorial in the denominator, those are 1. Together, those cancel to 1. All right, so this one, quickly. So now in a sequence. So what is 2i minus 1 factorial? So it'd be, the first would be 2i minus 1, and then times what? What would be the next thing we'd multiply that by? It'd be the number that's 1 less than this, right? Which is? 2, right? And then 1 less than that would be? And we would keep going like that until we reach what? Always down to 1. Right, what's 2i plus 1 factorial? 2i plus 1 times 2i times 2i minus 1. Are you following this? You always just subtract 1 from whatever you have to get the next thing you multiply by. So I'm just subtracting 1 each time, just like we did up here. We just subtracted 1 as we went down. All right, so 2i minus 2. So what do you notice? Within 2i plus 1 factorial is? 2i minus 1 factorial is right here. You see that? This is the same as the numerator. Therefore, the sequence is the same as 1 over 2i plus 1 times 2i. There's another way to write that sequence without factorials. Does it converge or diverge? Definitely converges. It's kind of, it's like a p sequence with p equal to 2. Two I, or 4i squared. You're going to have 4i squared, so your p value is 2.